lecture we will discuss a little bit more about quasi Fermi levels. As I had mentioned that quasi Fermi levels are very important in optoelectronic devices. Normally in PN junction diodes we do write quasi Fermi levels, but we don't discuss much. But in optoelectronic devices, as you will see, it is the difference between the quasi Fermi levels which will determine the bandwidth of a semiconductor laser amplifier. So what are quasi Fermi levels? It refers to the two Fermi levels which describe the probability of occupation in the conduction band and the valence band. In the conduction band and the valence band. Now there are two, that is why for quasi Fermi levels, valence band in quasi equilibrium. Hence the name quasi Fermi levels. So it refers to the two Fermi levels that describe the occupation probability of electrons in the conduction band and in the valence band. One Fermi level to describe the occupation probability in the conduction band, and another Fermi level to describe the occupation probability in the valence band when the semiconductor is in quasi equilibrium. So we will see what is this quasi equilibrium, but before we go to quasi equilibrium, let us first discuss the thermal equilibrium. Thermal equilibrium refers to a steady state, an equilibrium, a steady state at constant temperature, and when there are no other sources of excitation. So the energy is supplied, the energy under consideration is mainly thermal energy. So let us first see at thermal equilibrium what are the electronic transition processes in a semiconductor. So at thermal equilibrium, it's an equilibrium, it is not static, it is dynamic, but there is an equilibrium. So if you recall the energy band diagram, so this is EV, EC, we have large number of allowed states in this band, and the density of states go on increasing as you go to higher values. Similarly, there are density of states here, and the density of states become more and more, which means they are becoming denser and denser as you go further down. So EV, EC, and separated by EG. This is the valence band and this is the conduction band. Along with this, we can also plot the EK diagram. The EK diagram, where this is basically a large number of allowed states here, almost continuum, and large number of states in the lower band as well. So both are equivalent picture. This is EK. At thermal equilibrium, when T is equal to 0 in a semiconductor, in T equal to 0K, the lower band is completely full and upper band is completely empty. And at a finite T, there are electrons which are making continuous upward transition. Please remember, it is not that there are some fixed number of electrons here and fixed number of holes here. It is a dynamic equilibrium. There are electrons which are making upward transition and downward transition. In the presence of at a finite temperature T, electrons are continuously getting excited to the conduction band, and also they are recombining with the holes. But there is a steady state. At steady state, number of electrons making upward transition is equal to number of electrons making downward transition. This is the steady state. It does not mean the electrons are, they are continuously in a state of transition upward and downward. But there is a equilibrium. At equilibrium, there is an average number of carriers here and an average number of carriers which are present here. In this, so there are electrons which are making transition, upward transition. It could make upward transition here also, and also there are electrons which are making downward transition. Usually, if an electron which makes a transition to a higher energy level here, it will rapidly come down within the band by a process called thermalization. This is due to phonon transitions. An electron excited to an upper level in the conduction band rapidly comes down to lower vacant states by the process of thermalization. Thermalization means it gives energy to phonons, and phonons are quanta of lattice vibration. So, and it rapidly comes down here and it accumulates at the bottom of this band. Although it may be making a transition upward, it comes down and accumulates here. When the electron has left this place, there is a hole here. The hole is at a higher energy. So the electron which is sitting here comes down to the position of the hole, and the hole makes an upward transition here. So the hole also similarly makes transition upward to the top of the band. Hole has lowest energy when it comes to the top of the band. So the holes accumulate near the top. So yes, at steady state, when the number of electrons going up equal to number of electrons coming down, there is a certain number of holes here and there is a certain number of electrons in the conduction band. That is the carrier concentration which we talk of at any given temperature T. The phonon transitions are very, very rapid. Typical time for these transitions is tau is of the order of 10 to the power of minus 12 to 10 to the power of minus 13 seconds. This is the transition time, recombination time, that is the time over which the electron comes down by thermalization, or this is called the intra-band recombination time or intra-band carrier time, carrier lifetime within the band, intra-band. So the intra-band lifetime here refers to the time over which it is at an excited state. It's not lifetime of the electron within the band, intra-band lifetime, or it is also the same as recombination time, or it is also the same as the photon transition time. So that means this is extremely rapid. It comes to the bottom. The transition time here, that is from the conduction band to the valence band, typical time tau, that is interband transition time, is of the order of 10 to the power of minus 8 to 10 to the power of minus 9 seconds. The interband transition, which means the intra-band transition is much, much faster. Therefore, at any time, although there are continuously transitions taking place, at any time you see a steady state. You can imagine this by an example here. You take a container. Please see this example, an example of water tank and pump. Water tank and pumping. So I have a container here. All right, let me draw it at the same level as EC. Just a second. This is not band diagram, this is a container. So there are two containers, two tanks. So this is a tank where there is water. I am describing the process of thermal equilibrium with the analogy of water in a tank. At T is equal to 0, the lower tank is completely full. Upper tank is completely empty. This upper tank has holes. There are holes here through which if I pump water, it can trickle down. So these are holes in the upper tank. The lower tank does not have any hole. I now take a pump. So this is a pump P1, pump P1. When the pump is off, this tank is full, this tank is empty. I switch on the pump, so the pump is pumping water here, so water is falling down and water is flowing down here to the bottom of the tank. And there are holes, therefore water is also trickling down. The water is also falling down. Because I am pumping up into this tank, water is getting accumulated here, but it is also flowing down through these holes. If the holes are sufficiently small, if they are small, then there will be some amount of water which is accumulated in this. The amount of water here, the level of water here depends on the pumping rate. If I pump very slowly, very small amount of water is entering this tank and it is also going down. So the new steady state, when the pump is on, the new steady state is this, that the water level has come up to this. There is no vacancy here and there is water up to this. You compare this water to electrons and the vacancy is to holes. So electrons are pumped up because of temperature, because of thermal energy, the thermal pump. So this pump is for thermal energy. So I want to call this as thermal pump or temperature pump. A pump because of thermal energy. So there is a steady state here. You can imagine bucket of water also. You take a bucket of water and there is a hole from the side, leave the tap into it. Depending on the rate at which water is falling in the bucket, the hole is very small, so there will be some steady level. You increase the rate of flow, the level will go up, and of course here it will go out at a faster rate, because whatever the steady state is, the amount of water which comes must be equal to the amount of water. It's exactly like this. At finite T, the pump is off is equivalent to T equal to 0. So T equal to 0 K implies, is equivalent, it's not implies, it is equivalent to pump P1 off. This tank is completely full, this tank is completely empty. This band is completely full, this band is completely empty. You switch on the pump, so now we are at a finite temperature, some value T equal to, let us say, 300 K, which is equal to pump on, P1 on, at some rate, and therefore you have some level which is steady level. If I increase the pumping rate, that is, if I increase the temperature from 300 to 400, if I increase the pumping rate, it means it will now go to a new level. So more water is coming, so it will fill here, this level will go down, and you will have a new level which is here, and this is here. This is carrier concentration, temperature dependence of carrier concentration. Now, why did I bring this concept? At a given temperature, I may have a second pump, not the temperature pump. Temperature is fixed, 300 K. But I have another pump, so I use a second pump. From here, and which is also pouring water into this. This is pump 2. Pump P2, which is also lifting water and pouring into this. This is not the temperature pump. So it is not now, because water is coming from here also, the level will now change to a new level because there is more water which is being pumped. So this comes to a new level. And similarly here, this goes down to a new level. So this is the new level. This is with P1 plus P2 both on. P1 plus P2 on. This level is with P1 on. Same thing is true here also. So P1 on. And this level is when P1 and P2 both off. What is the point? The point is, when you have a second pump, there is a new equilibrium. The levels are different now. There is a new equilibrium. There was no change in temperature. So it is not temperature pump. The normal Fermi function describes the occupation probability of electrons at thermal equilibrium. It describes occupation probability for both conduction band and valence band. But when you have a new equilibrium in the presence of an additional pumping source, what is this additional pumping source? We will see. When you have pumping, an additional pumping source, one Fermi function cannot describe both of them because you have simultaneously very large number of electrons and very large number of holes, a large vacancy. In this tank, water has gone down because half the water is here. So you have, but this rate at which the water is falling is much slower compared to the rate at which water is settling down here. Why does it have a steady state here? You imagine the bucket. If the bottom of the bucket is open, no matter what the rate at which you pour, there will be no water in the per bucket. There is no steady level at all. But if the hole is very small in the bucket, or if the rate at which water is going down from here is much smaller than the rate at which it is pouring down and settling quickly here, then you have a steady state distribution here and a steady state distribution here. each one of them can be described by the Fermi function. But you need two Fermi functions, one to describe this and the another one to describe this. Why two Fermi function? Because the number here, the carrier density here is so large that you have to bring the Fermi level here up. You know, in a semiconductor, if the number of electrons here is very large, like in n-doped semiconductor, the Fermi level is shifted up because I want to describe the probability like this. If it is p-type, then the Fermi level is shifted down. So if it is p level, p-type, where you have large number of holes, then the Fermi function is shifted down. So this is 0.5 probability. So 0.5, what I have plotted is f of e versus e. Always the vertical axis is e. Sometimes I might not have marked what is the vertical axis, but always, everywhere, vertical axis is e. So this is f of e. So this is a n-type and this is a p-type. Now we have a situation where we have large number of electrons and large number of holes simultaneously. And this can be described, and all at steady state. They are at steady state because the time, this time here, where the rate at which transition is taking place is much smaller compared to this time, which is causing stabilization, rapid stabilization or rapid thermalization. Therefore, at any time, if you take a photograph, there is a steady level sitting here, there is a steady level sitting here. It's steady state. Therefore, if you use two Fermi functions, one to describe the population of the valence band, one to simultaneously, one will be here and one will be here, two Fermi functions. These are called the quasi Fermi levels. In the same semiconductor, here it was n types, another semiconductor, here it is p type, separate semiconductor. But now you have a situation of quasi equilibrium where you have an additional source of pumping. You have two Fermi levels to describe the population of the two bands, and these are called the quasi Fermi levels. Is this picture clear? That this is at 0K, no pump, P1, P2 both off. The lower band is full, upper band. This way I have plotted it equivalently, just by the side. Here the level goes down, which means there is vacancy here. That means there are holes here. The vacancy here, air gap, is like holes, and water drop is like electrons. This is a very good analogy. At every stage, you will see later on, there are complicated band diagrams where you can understand them every time you think that electron is like a water drop, because water drop always flows from a higher level to a lower level, whereas air bubble always goes from lower to higher level. So you will see that this picture will definitely be very helpful. So let me rub this off, and so under the condition that the intra-band transition time or thermalization time is much smaller compared to the interband transition, you will always have a steady state distribution. And that steady state distribution in the two bands can be described by two different Fermi functions called the quasi Fermi level. So we have at thermal equilibrium, again let me plot EV, EC and E versus f of E, the Fermi function, and you have a distribution so this is 1.0, so it's 0.5, f of E equal to 0, 0.5, you draw the vertical line where it intersects, that gives you EF. So this is at a particular temperature T, T greater than 0, T greater than 0, 1 F of E, describing the probability of occupation of the conduction band and the valence band. And F of E is given by 1 divided by e to the power E minus EF by KT plus 1. In quasi-equilibrium, now you have an additional source which brings in more electrons to the upper band, and therefore you have I'm sorry. This is where you don't have anything. I could have kept a drawn figure already for display, but I thought if I plot it in front of you, you will know what is the difference now. So this is EFC, Fermi level or Fermi function describing the conduction band, occupation probability of the conduction band. This part has no role, only this upper part has a role to describe the population of the conduction band, occupation probability of electrons in the conduction band. Here, this is at 0.5. It so happens that it comes out at the same value as, by chance it is at EV. So EFV is here. This function describes the population of occupation probability of electrons in the valence band. So this is F of E, and this is 1 minus F of E, which describes the occupation probability of holes in the valence band. Two functions are separate. So this is called FV of E, and this is FC of E. One Fermi function describing the occupation probability of the conduction band, and a second Fermi function describing occupation probability of the valence band. FC of E. Okay, let me write on this side. This may go out of view. Let me erase this picture. Where Fc of E, so Fc of E is equal to 1 divided by e to the power E minus EFC by KT plus 1. So instead of EF, we have EFC, and here we have EFV. So FV of E is equal to 1 divided by e to the power E minus EFV by KT plus 1. Is this okay? Is there any doubt?
EFP and EB always coincide. That dotted line and
No. I went on saying that it is just by chance in my diagram it came out to be coinciding. It need not, it does not, or need not. In general, it does not. But by chance, the way I have drawn it, that 0.5 thing came out to be at the same value as EV. But there is no relation at all. So, this is EC and EV. By chance it is there. But the important point that you get is one Fermi function characterized by one Fermi energy EFV will describe the occupation probability of the valence band, and therefore 1 minus FV of E will give you the occupation probability of holes. And a second Fermi function simultaneously in the same material. This is not one is N type, one is P type. It is the same material, but it is now in quasi equilibrium. When a material is in thermal equilibrium, you will describe it by one single Fermi function. When a material is in quasi equilibrium, which means there is an additional source of pumping, additional source of excitation. This additional source of excitation could be radiation, a semiconductor which is illuminated by light, or it could be the PN junction where carrier injection is taking place, and at the junction, in the junction region, you are pouring in electrons and holes. So, if you look at that junction region, there are simultaneously large number of electrons and large number of holes. This is carrier injection, and you have two Fermi levels in that region. Before I proceed to the excitation mechanism, more about the excitation mechanism, under Boltzmann approximation, we had an expression for carrier concentration N is equal to Nc into e to the power Ef minus Ec by K at thermal equilibrium. In quasi equilibrium, everything remains the same. If we still meet the Boltzmann approximation, this is a clause, because EFC, if it is still somewhere below here, then I can still use EFC and I can still use Boltzmann approximation, and then this will become, so this is at thermal equilibrium. In quasi equilibrium, the same expression is valid with EF replaced by EFC minus EC by KT. Simply the EF is replaced by EFC, because what was EF doing? It was describing the Fermi function. Now the Fermi function is described by FC of E, which means EFC of E. And P, the carrier concentration of holes, is Nv into e to the power EFV minus EVO. EV minus EFV by KT. Let me write the two expressions again, because it's a little congested there. And therefore, N into P is equal to Nc into Nv into the product of these is equal to e to the power minus Eg by Kt. N into P is Nc into Nv, e to the power Ev, e to the power minus Ec. Therefore, it is minus Ec minus Ev, therefore minus Eg by Kt into, what do we have? There is a second term, e to the power, let me go further, into e to the power EFC minus EFV by Kt. What is this term? It is Ni square. This term is Ni square. Therefore, this is equal to Ni square into e to the power EFC minus EFV by kT. So, N into P is equal to this by kT. In thermal equilibrium, EFC is equal to EFV equal to EF. There is only one EF, which means this is 0, the numerator here, because EFC equal to EFV, there is nothing like two Fermi functions, only one, and you are NP equal to Ni square in thermal equilibrium. In quasi equilibrium, we have two Fermi functions, and I mentioned that it is the difference between these. Therefore, if EFC minus EFV is greater than 0, if the difference is greater than 0, then NP is greater than N. The number of carriers that we have, the product of carriers is greater than Ni square. And if this is less than 0, when will this be greater than 0? When will this be less than 0? I will show you with the p-n junction now. But if this is less than 0, so if EFC minus EFV is less than 0, that means EFC is below EFV, EFV is above, less than 0, then we have NP less than Ni square. Under Boltzmann approximation, which means we are considering relatively lightly doped p-n junction and relatively lightly doped p-n material, and our quasi equilibrium is quite mild. So in quasi equilibrium, the law of mass action is not Np equal to Ni square, but N into P equal to Ni square into e to the power of EFC minus EFV by kT. Let's quickly take the band diagram of a p-n junction and see what is this. We will discuss p-n junction a little bit more in a later class, but let us quickly take up the band diagram and see. What will be the situation when this is greater than 0, and when will be this is less than 0? All of you must be familiar with the p-n band diagram of a p-n junction. I hope. We will see. p-n junction. So I am drawing the energy band diagram of a typical p-n junction. So this is p-type material. So P, and this is L. And we have at equilibrium, we have one Fermi level, EF. So this axis is energy, E, and this axis is the distance, x. So x, you can take x equal to 0 at the junction, the metallurgic junction between p-type material and n-type material, and there is a energy band variation. So you have plenty of electrons here. So plenty of electrons, water. So whenever electron comes, just think of water, very easy to follow, and plenty of holes, air bubbles. And near the junction there are neither holes nor air bubbles, or very little electrons and holes at the junction, which we usually call as the depletion region. In electronics, we usually call this region as the depletion region. But in optoelectronics, we don't call it depletion region, because for optoelectronic devices, this is the most important region, and we call it the active region. It is called the active region. Depletion region gives a little bit of a negative this and that, oh, it is depleted. But it is the most important region, which is the active region. So you have one Fermi function, this is the P end. Now you forward bias this, which means to the P end. So let me show the, so this is the junction P end. Now you apply a forward bias. This is the entire PN material. I am not showing just the junction. So PN, we apply a forward bias. So when we apply a forward bias, what happens? The right side goes upwards with respect to the left side, because electrons get more potential energy. It is connected to negative terminal. So electrons now have a higher potential energy, and this is energy axis. So this end starts moving up relative to this end. So we have a forward biased PN junction, and the band diagram now, so originally it was like this. So now it has been lifted up from the original position. Relative to that, so this was its original position. So let me not show the original position. So this is after forward biasing. So forward biased junction. What happens to the Fermi function? So Fermi level in this side remains where it is, far away from the junction. There is no potential felt. So Fermi level is here, and far away from the junction, the Fermi level is here. What about the junction region? So this, so in the junction region, you see there are two Fermi functions. In the junction region, now this is the moment you forward bias it, which means in addition to temperature, you are injecting, you are giving it supply from outside, which means you are introducing carrier injection. Then in the junction region, what has happened? This has gone up. So when this has gone up, water has started moving here. You see, the level has been raised. So water has come into there was earlier a gap, depletion region. Now when you have raised this, water is moving this side because the barrier is lowered. And what happens to the air bubble? So this has, imagine here itself. So if this goes like this, air bubble can come here. So exactly like that, you have air bubbles coming into this side, which means you look at the same original junction and the new forward bias junction. You have lot of electrons and lot of holes in at the same value of x. Means at the same physical position, you have simultaneously large number of holes and large number of electrons. This is quasi-equilibrium. This has come up because of the external power source, because of forward biasing. And accordingly, you see that there are two Fermi functions here. And this is now EFV and this is EFC for the junction region. And therefore, as far as if you focus only on look at the junction region only, it is a region where you have simultaneously large number of holes and large number of electrons, and it is described by two Fermi functions. The separation here, EFC minus EFV, is positive. EFC minus EFV is positive. EFC minus EFV is greater than 0, which means in this junction now N into P is greater than Ni square. You have simultaneously large number of carriers. When will we have this kind of the second type of situation? If we reverse bias. So if we reverse bias the junction, then this will further go down, which means this will remain there, but the other portion goes down. So let me erase the forward bias, and the band diagram now becomes, so it goes down further. The N still remains here, EF, but in the junction region, this is EFC, and EF is here, far away for the P type and N type, but in the junction region, EFV is now here. So if we look at the junction region, this is EFV and this is EFC. EFC. The difference now is negative. Obviously, when you reverse bias, the depletion region further widens and carriers are pulled back, and you have much less carriers in the depletion region. In fact, the forward biasing is the principle of realizing optical sources, and reverse biasing is the principle of realizing optical detectors. As we will see later, that this is the case corresponding to optical sources, and this is the case corresponding to optical detectors. So we will pause for a while here about the basics, and most of the basics, essential basics which are required for this course, we have reviewed. A little bit of PN junction, we will discuss a little later, not because of the normal PN junction which you have already studied, but we will have to deal with the homojunctions, heterojunctions and double heterojunctions, and we will need to know how to draw the band diagram in the case of heterojunctions. It is very easy in the case of PN junction, we simply draw it like this, but what happens if you have a heterojunction? That is a junction between two dissimilar semiconductors which have different band gaps. How to plot even the PN junction band diagram, energy band diagram? So we will discuss this a little later, but before that we will take up our next topic, will be semiconductor materials. As indicated again, that our focus will be mainly on optoelectronic materials. Not all semiconductor materials you would be interested, particularly materials for optoelectronics. Maybe we stop at this point because we are now changing over to the material aspects. So we will discuss about heterostructures and ternary compounds, quaternary compounds, and band gap engineering, band gap modification. These will be our topics in the next two classes. Do you have some questions? Any question? All right, so I will stop here.